Here we go. I'm going to go ahead and record this just so we can have some notey notes later. Maybe for Rudy. Maybe he'll actually watch them this weekend. Let's pose a question. Hey, everybody say hi, Rudy.
Hi, Rudy.
We miss you, Rudy. Okay, maybe not. All right. Some reactions occur rapidly, such as the inflation of an airbag. That process is the formation of sodium, the decomposition of sodium azide, Na3N, sodium azide. And guess what gas fills it up? If we decompose that, what gas is inside of an airbag? What gas would be inside of the airbag if we decompose that? Nitrogen gas. You have sodium and nitrogen on the other side. Explosion of nitrogen triiodide. You can do that with a simple feather if you dry it off. In here, we actually blew some of that up in college by accident.
That sounds like something Rudy would do.
Probably. It's like mixing up some nitrogen and iodide. Yeah, iodine.
Where does the azide thing come from?
This is what this is called. This is just a common name for that. Common name. All right? And some reactions occur slowly, such as reaction of pigments and paintings with light and pollutants. As we know, the Mona Lisa is not as good as it is today as it used to be when it was made. Tarnishing of silver and iron rusting. Right? Iron doesn't rust overnight. Right? You can leave a car out there for a while, one of the old classic cars. All right, so here we go. Let's see. All right, rate of reaction. So what are we going to be looking at? An increase in the concentration of one of the products per unit time, or the decrease in concentration of one of the reactants per unit time. If we make product, what are we going to have less of? If we make product, what are we going to have less of? Reactants. All right, that's what this is all about. Or how fast reactants are being converted to products during a chemical reaction. Either the rate of formation of the product of rate of production, or the rate of consumption of a reactant may be used. Sorry about that. That's what I was making a 56 slide PowerPoint last night. I'll probably type that pretty quick. They're related to each other by dividing the corresponding coefficient in the stoichiometric equation. So dividing the corresponding coefficient, what you started with and what you're going to, you look at the coefficients. All right. What are the units that we're going to use that you need to know? Mole per liter per second. So this is what it looks like. So mole per liter second. So if you were doing the math, that's what it would look like. IB will list it most of the time as this. Mole, all right? And then they'll do this. Liter to the -1, second to the -1, all right? So that's the same thing, so don't get confused by what the unit is. All right, those two are the same. So you'll see it a lot like this. All right, just like this. Or decimeter to the -3, which is what? 1 decimeter cubed equals what? 1 liter. Okay, so then I have this one down here as well. You'll see that. You'll see this one more in IB, more in AP. All right. All right, define the term rate of reaction. All right, so let's take a look at this reaction that we have here. We have a bunch of red balls. We have blue balls, and we have red balls, and blue balls, and red balls. All right, so what we have here is rates of reactions can be determined by monitoring the change in concentration of either the reactants or products as a function of time. So what we have here that you need to know how this looks, this means, what does that mean right there when I have brackets around something? What does that mean? What does that mean? Yeah?
Doesn't it be like, I don't know, in like round up or round down?
For math, but this is chemistry. Yes, for math it does, but not for this. I'll give you a hint. It's in here somewhere.
Concentration.
Concentration. So anytime that we do brackets, we're talking about the concentration of something, and that's usually in molarity. All right, so you don't have to put in 6.7 molar or 1.0 moles. You don't have to do that. So if we were to do this and pull this first one out, we would have the concentration of A, and we don't have anything for B. So how could we list that? If we wanted to say there's no concentration, raise it to the 0, which equals 1. Right? If you didn't want to say it. You don't have to even include this. So if I'm just looking at the first one, it'd be concentration of A. This one will contain both A and B to a certain amount. A to a M and B to an N. And the same thing with the next one. It's whatever power it could be. You don't know what power it's going to be right now. Nothing here is going to tell you what power it's going to be. They're just saying it would be raised because there's both A and B present. When there's not, and there's just A, when you're starting off at a reaction, you don't include this at all. All right, you don't include that at all. All right, okay. So then we monitor that as a function of time, the change in the concentration of A versus time. So we divide them. All right, we divide them, or the concentration of B versus time. All right. Every day is a blessing when you don't feel good. Every day is a blessing. All right, how fast does a reaction happen? How could we measure that? All right, we need an indicator that a reaction is happening. So these guys are what we need to be including for our chemical changes in our labs. All right, these indicate a chemical change has occurred. And those are color change. Anytime you have a color change, gas evolution. How could you tell if gas is being produced?
It's giving off.
Well, if it's not giving off a gas, how could else you tell?
Decrease in mass.
Decrease in mass. What else? What else? What's the easiest way to tell that gas is being produced?
Here, I'm looking at it.
What do you mean? What are you looking at?
The reaction.
What's associated with gas?
If that's ice, that's not good for you.
What's associated with gas? Ice is not good for me?
No, because it'll make your frozen.
Okay. Yes.
Well, a certain temperature is needed in order for a gas to reach, in order for there to be a gas that's the boiling point. So if there's a
What happens when water boils? What do you see?
Vapor.
Before that.
Bubbles.
Bubbles!
Oh.
Bubbles! So if you have a very weak reaction, but you see bubbles, you have gas production. All right, so if you see bubbles, all the other things that you guys are all high level. Sometimes I can see some bubbles popping, I'm like, oh, there's some gas. All right, precipitate formation, what is that? What is that again? Yes?
It's when like a solid forms.
All right, two liquids form a solid that is insoluble. So insoluble solid. All right. And then heat and light. That should be pretty self-explanatory. All right. In many cases, it is easiest to measure how fast the product is appearing. And we did that. We all did that. We did somewhat similar example of this equation right here, where you form the carbon dioxide gas. You measure how much is given off, how much you lost in a reaction. It's very easy to measure. There's another way to do it. The easiest thing to measure here would be probably the carbon dioxide. We could collect the CO2 in a syringe and measure how the volume changed over time. The rate would be the change in volume over the change in time. So you just take the change in volume divided by the time. We can also measure how fast the reactant is disappearing. Okay? So there's many different ways to do that. Would it be easy to do a syringe? Well, you'd have to take, if I wanted to do this, now it's good that you kind of know after the fact, IB you're supposed to discover on your own. I would have taken a flask, the little flask that I had, right? I would have put a rubber stopper on top. It had a little hole in it. It had a tube going in here. and then attached to a syringe, right? So then I have my syringe off the side, and then you can really measure how much you have. I mean, no way you would have done that, but just saying, this is another way to kind of think about things for future, or if you have to set up a lab on part 2 or paper 2 or paper 3 of your test. All right? So kind of star that just so you remember what it looked like. All right, next, measuring the rate of reaction. There are many ways to measure it. Change in mass over time. Yeah, we did that. Didn't everybody do that on their lab? They could, I think so, yeah. Change in mass over time, change in volume over time. You could have done volume as well, because you could have measured the amount of, pre-measured the amount of reactants you had, and then post-reaction measured how much volume you could have. You could have done that too. Liquid has volume. Change in concentration over time, which would have been a little bit harder to do. Okay, you could have done it. Yes, you could have done it with a titration. Perfect. All right. I'll put it in here for you. That was a good poll. All right, so you can do that with a titration, and then of course that happens, right? There you go. All right, change in pressure over time. We can use a change in pressure because of the ideal gas law. All right, and we can say that pressure, because of the ideal gas law, pressure is a unit of concentration. So if you get a problem that gives you torr or kilopascals, you just consider that a unit of concentration. But there's not really much math in chapter 6. But you could get that. All right, so pressure, because of the ideal gas law and all the ramifications there, you can say pressure is a unit of concentration. Change in pH over time, change in color. You have to use a spectrophotometer or colorimeter. We only have spectrophotometers. Of course, you can fire that up anytime you want. And the change in conductivity over time, which is what Rudy likes to try to do. For some reason, produce electrical
I
current.
think he's hoping he'll like shock himself.
Yes. Somebody tell me when it's 9:35 on that clock. All right. All right, so let's describe 6162. Describe a suitable experimental procedures for measuring rates of reactions. Okay, so you have to imagine paper 2. What could we do to describe a suitable experimental procedure for measuring rates of reactions? Well, you did that. You set one up. Now you know how to modify it. I showed you how to modify it. So you should be good on 6162, 6.162. All right, rate is, okay, so if we did this, change in pressure over the change in time equals the change in the concentration of the reactants. That's what this is. Excuse me, this is products. Change in products over the change equals the change in reactants. Now, notice this right here. What are you noticing different about these two?
One's negative.
Why? Why is this negative? And why is this positive? Yeah?
Because since you're starting out all reactants,
Uh-huh.
you want to lose a significant portion of products, which will give you a negative answer. You don't have the negative.
Remember, these two are separate. Make sure you know they're separate. So what we're doing here is when we react, we only lose reactants. So to do that, we have to have a negative value because we're only losing them. In products, we are forming. So when we form something, it is positive.
Oh.
All right, it is positive. One second here. I'm going to pause this. Change that